Hi, it's Paul Anderson, and this is Chemistry Essentials Video 6. It's on periodicity. In other words, it's going to be the patterns that we see in the periodic table. Now, what determines that is going to be electron configuration, and we can figure that out using the Aufbau principle, which is actually German, and it means the principle of building up. So we're building up from lower to higher energy levels. And so what we can find is these trends that start to emerge, but it's most important, instead of just memorizing them, that you really understand what's going on inside the atom that determines those trends. And so periodicity, remember, is going to be derived from the electron configuration, in other words, where the electrons are. And we can determine that by using the Aufbau principle. And if you were to watch the last video on electron configuration, I think that'd help a lot. But what's the meaning behind this? It all comes from Coulomb's law, which helps to explain electron configuration, and also helps to explain these trends. It explains changes in the ionization energy, changes in the atomic and ionic radii, how big the atom or ion is, electronegativity, and finally the ion charge. And so if you really understand Coulomb's law, you can kind of work your way through this on the periodic table. Why is this important? We can use the periodic table to make predictions, especially about things that we haven't even designed yet. And so if we look at the periodic table, this on the right side is going to show us which of these are going to be filled over time. But if you look at the periodic table, we'll find trends. And so here's hydrogen. What we really need to do is take helium and then put it over in this S block. It's going to make us, it's a little easier to understand. And so what we're going to have are energy shells, and then these would be subshells within that. And so one thing you should understand about the periodic table is that this F block should slide right in here. It'd be hard to write a convenient periodic table, but that's really how it should be set up. Generally, we've just put it down below. And so what's guiding this or explaining the electron configuration, remember, is Coulomb's law. And so it's pretty simple. If we look at the protons on the inside of the nucleus, they have a positive charge. The electrons have a negative charge. And so Coulomb's law says we just multiply those. In other words, the bigger they are, the bigger the force between the two is going to be. But as we increase the radius, the distance between the nucleus and those electrons, then we're going to see a decrease in that force. The one thing that you have to add to that is that once we fill up one of these orbitals or subshells, it's going to shield the electrons on the outside from those on the inside. So let's get started and work through this list. What's going to happen to the ionization energy? Well, let's look at Coulomb's law. Ionization energy is the energy required to pull one of these electrons away. And so what's going to happen as we increase the size of atoms, we're going to increase the number of protons, and so we're going to make it harder for you to pull an electron away. And so we move across the periodic table, we're going to see an increase in ionization energy. What's going to happen as we go down the periodic table? Well, as we go down the periodic table, they're getting bigger and bigger and bigger, and so the radius is going to get larger. And so therefore, we're going to see a decrease in ionization energy. So you can think of ionization energy going up and to the right. Now, it's not as simple as this. What we're really looking at is within subshells, we're going to see that pattern, because you'll see changes within here and orbitals as well. But it's just a general trend, and it comes from Coulomb's law. Let's look at atomic and ionic radii. Well, what happens as we increase the atomic number? We're increasing the number of protons. What is that going to do? It's going to pull it in. In other words, it's going to pull those electrons more closely to the center. And so it's actually going to be the opposite. It's going to increase as we go down, and it's going to increase as we go from the right to the left across the periodic table. And so you can see this graph of atomic radii is actually going to be the inverse of what we saw with ionization energy. What about electronegativity? Electronegativity is how much an electron, and it's bad to say this, but wants an electron. In other words, how much it would like to receive another electron. Well, remember, as we're going across a subshell, let's say we're going across this P block right here, as we go across, we're increasing the number of protons, and therefore we're increasing that pull of the nucleus on the electrons outside it. And so as we move from the left to the right, we're going to increase how much that atom wants an electron, at least until we get to the noble gases. And so electronegativity is going to follow ionization energy as well. What if we look at then ionic charge? Well, to look at ionic charge, we really have to look at how close an atom is to a noble gas. And so let's throw noble gases up here. Noble gases are going to have a full inner electron subshell, and so anything that moves you towards that is going to make you a more stable atom. And so remember, the only atoms that exist by themselves are going to be the noble gases up here. So a quick way to figure out ionic charge using Coulomb's law is to just look how close you are to a noble gas. And so let's look at the halogens, which are right here. How many electrons would halogens have to get in order for them to move to a noble gas? Well, just one electron. And so they're going to have, in general, a -1 charge. Let's move over. These would have -2, -3. Let's go way to the other side with the alkali metals. What about them? Well, it would be hard to go all the way across here to get to the noble gases. It's just easier to go around the back. In other words, they could lose the electron, and when you lose the electron, you have a +1 charge. And so we could kind of work it up in this direction as well. And so again, it's not hold fast. In other words, these are general trends, but they can all be predicted just by applying Coulomb's law. So it's hard to talk about the periodic table without talking about Dmitri Mendeleev, who's really the father of the periodic table. But you've probably never heard of Julius von Meyer, who was a German who was working on the periodic table at the same time and published his periodic table around the same time as Mendeleev. Now, why haven't you heard of Meyer? Well, Mendeleev made these huge predictions. In other words, here's his periodic table. And you see here that he had some question marks where they hadn't identified those atoms. What he did is he would predict them. And so he predicted germanium, and he called it ecosilicon. And here are all the predictions he made about the properties of this ecosilicon. And if we look at his predictions and then compare it to the actual values all the way down, you'll find that he was pretty much spot on. And that's why Mendeleev is given credit for the periodic table. Not only was he able to build it, put it together, but he also made these great predictions, and his predictions were spot on. And so that kind of lends to this next topic I wanted to talk about, which is material design. What we can do is we can take things off the periodic table. So let me grab some atoms. Let me grab some silicon and some oxygen, and so we make some silicon dioxide. And when we do that, we get a ceramic. A ceramic is going to be build up maybe stoneware or earthenware. So it's going to build up these tiles over here on the side. And so if silicon dioxide can make that, well, what about something below that? What about tin? If I were to grab that, I could say maybe those are going to form ceramics, and they will. They'll form glazes that are going to be on these ceramic tiles as well. And so what scientists can do is they can dance around the periodic table, and if you know some of these trends, you can make predictions about new materials. And so again, in summary, periodicity comes from the electron configuration, which is determined by the Aufbau principle, but what really explains it is Coulomb's law, which allows us to make these big predictions. Ionization, remember, goes up and to the right. Atomic radii increases down and to the left. Electronegativity up and to the right. And then ionic charge, remember, we find where the noble gases are, and then we look at how many electrons we have to gain or lose to get there. And then these are important in designing materials. So you should have learned to predict or justify trends in atomic properties. Where would I point you if you didn't get that? Remember looking at this chart and seeing how ionization and electronegativity change. If we were to look at justifying the arrangement based on reactivity, it all goes back to Coulomb's law. And remember, the bigger the charges are, the bigger the ionization energy, or the bigger the force holding the electrons in place is going to be. But there's also the shielding effect. And then remember, we can identify patterns to predict design. And the example of silicon and tin oxides are an example of that. So that's periodicity, and I hope that was helpful.